So let me present my screen also. Right. I hope I'm audible and my screen is visible, right? Right. So let's begin from where we have left last time. So we were looking at different aspects of models, okay, program models that we were looking, and we were trying to actually look at the different kinds of jump instructions. Okay, so these are logical instructions: jump above, jump not below or equal. Okay, all these are logical instructions where or logical comparisons, or and also another thing is these are unsigned comparisons. Whereas jump JG, JNLE, JGE, JNL, these are all signed comparisons. Okay, so in this we will take into account the sign flag also into picture. Okay, so for example, when I have JG or JNLE, both are equivalent. Jump if greater or jump if not less than or equal to. If not less than or equal to is what? Greater only. Okay. So what happens when you actually do JG? Okay. For example, if you have a comparison like this, and after comparison, let us say you have JG. Let us say I have an instruction like this. I have the two set of instructions: CMP, AX, comma BX, and then I have JG L1. Let us say L1 is a variable. L1 is a label, right? So now what happens is it will do a comparison of AX and BX, okay? And it will do it will take action, that is, it will jump to this location L1, okay, if the following happens. Okay, sign flag and auxiliary and overflow flag, the XOR of it is 0, and Z flag is zero flag is 0. Okay, so how does it happen? So now if AX and BX, let us say that we have taken here some CX and BX, JG L1. Okay, now if CX is greater than BX, okay, CX is greater than BX, then what will happen is if you subtract CX from BX from CX, okay, you should get a non-zero result. You should get a non-zero result. Okay, otherwise it is not greater, right? If you should get a non-zero, so therefore zero flag should be 0. And further, when you do the subtraction, you should get the sign flag either as you should get sign flag and this flag is 0. That means what is happening is, if you let us say you have a positive number and you also have a positive number, both CX and BX. If you subtract them, if it comes to be a positive number, okay, then the sign flag is equal to 0. Okay, and if this, and in this case the auxiliary or overflow flag also, if it is 0, then you will be actually sure that both of them, or CX is greater than BX. If auxiliary or overflow flag, if it is 0, and sign flag if it is 1, okay, sign flag 0 and auxiliary and overflow flag is 1, that means what? Subtraction of two positive numbers has led to a negative number. When that will be possible? When will that happen? I'm subtracting BX from CX, and the result is a sign flag becoming negative 1, means negative number is coming up. When will that happen? When will that happen? Anybody? When will that happen? That will happen when your when BX is greater than CX. Only then. Suppose if you subtract 3 from 2, what will happen? You will get -1. Okay, the sign flag of this is sign flag of this will be 1 because it is a negative number. Okay, so that is why we are avoiding that case. In that case, if sign flag XOR XOR or overflow flag will actually become 1. If you XOR these two, it will become 1, right? So we don't want that to happen, or we are not looking at that case. So that is the case. Sign flag XOR overflow flag is equal to 0. Both should. That means this both sign flag and overflow flag are 1 or both are 0. Okay. When both are 0, we have seen the case. Okay. If subtraction of two positive numbers, okay, leads to a negative number, let us say that, okay, leads to a negative number. If it leads to a negative number and an overflow, okay, then what is happening? Because what this case will come. Okay, let me erase some place in my slides. Okay, so let us say that you have a negative number and you have a negative number, and you subtract it. Okay, subtract means this will become positive. So this will lead to a negative number in certain case. Okay, suppose let us say you have -8 and you subtract, let us say, uh, -6 from this. Okay, so this will be a -2. Okay, this is a negative number. Sign flag is 1. Okay, and overflow flag in this case will become how much? What will be the overflow flag in this case? Overflow flag will be 0. Okay, why? Because -2 can be represented in a in 8 bits or whatever it is. Okay, if we put it in, let us put it in the binary and do it. Okay, okay. So let us say that you have, let us do this way: -2 -8. Okay, if you do this, 2, how will you -2? How will you represent in the sign notation? Anybody? Anybody? 2, how do you represent in sign notation? Okay, if you put it in 8 bits, it will be this way. Okay, so 1 1 1 1 1 1 1 0, and 8. How do you represent 8? 1 0 0 is the this notation, and if you take the negative of this will become 0 1 1 1 plus 1. Okay, so 1 1 1 1 1 0 0. Okay, just give me a moment. Just give me a moment. Hello, sorry, there was some issue here. Right, coming back. So fine, when you actually do a subtraction from this, okay. So if we do even from the normal perspective, okay. So this will become yeah, one triple zero. If you add this to this, okay, or we should actually we are subtracting, right? So this will become plus 8. Okay, minus of minus 8 will become plus 8. If you add this, sorry, you should directly add 0 0 0 0 1 triple 0. Okay, if you add this, okay, 0, let me erase all these things. Okay, if you actually add this, so this will become 1 plus 1 1 0, then 1 0, then 1, and then 0, then there's a carry out. Okay, so this actually, did we make a mistake anywhere? One, did we make a mistake anywhere? 1 triple 0. This is actually 8. Oh, sorry. Sorry. This is minus 2. Okay. 0 0 0 0 1 triple 0. If I add this to it, okay. So this is 1 2 3 4 1 2 3 4. This is a carry out. Okay. Now, if you look at this, the sign flag is 0 and the overflow flag is also 0. Okay, and this is in fact the case where the cx, this, let us say that this is in cx, this is in bx. Okay, cx is greater than bx, minus 2 and minus 8 also. So sign flag was 0 and the auxiliary carry sorry, overflow flag was 0. Okay, both of them XORing will become actually 0. So both in positive numbers and negative numbers, we have seen this case that in fact, if the cx value is greater than bx value, signed even in the signed way, you will be actually having this particular condition, that is sign flag will and auxiliary carry flag, the XORing will become actually 0. Okay, if either of them is true, that is either sign flag is 1 or overflow flag is 1, then that will not be a case where the jump JG condition is not true. I mean, that will be the case where JG condition is not true. Okay, so I will leave this to for you to observe and conclude this. So basically, when JG will be taken is when this particular conditions are true. Similarly, when JGE, okay, we have to just remove the zero flag condition. When they both are 0, the zero flag will be 1. Okay, so JGE will be the case where if jump if equal to, okay, that will be case when sign flag and overflow flag, both of them are XORing, will become 0. And the lower JL, that is jump if lower, that is if CX in this case is lesser than BX. That is the case. Okay, so that will be a case where sign flag and overflow flag, the XORing will become 1. JLE is when you add the zero flag is equal to 1 condition also, or, and it is a or condition, not and. Okay, if JLE, if they are equal, zero flag is 1. Okay, then jump if equal, that is straight away you just have equal, that is zero flag is equal to 1. And jump if not equal is when zero flag is 0. So these two are straight away. Okay, so this is something which you can observe. You can take some examples and actually convince yourself that actually these are the flags that will be true, or these are the conditions will be true. Then when you are taking a jump JL or JNG and so on, right? Okay, let's go further.
Excuse me, sir.
Yes,
Sir, why do we need the JG when we have a A or instruction already?
right, right,
Because
right. Yeah,
according to
this
my
is where
observation, I have
that is
seen
see,
that the
see, actually the point is that when you want to do a signed comparison, you will use JG and JNLE and all those things. If you want to do an unsigned comparison, you will be doing JA, JAE, and so on. Unsigned comparison.
Yes, sir, but my observation has been like the carry flag is actually the XOR of sign flag and of overflow flag. If you see in the binary addition.
Now, see, I'll tell you something. Okay, this is something which I have done for our understanding. But what actually the microprocessor will do is what I have told you in the previous maybe 2 or 3 lectures back. Actually, it will do a subtraction with respect subtract. It won't do a 2's complement subtraction when it does the subtraction. It will actually do a kind of a subtracting binary subtraction. It will do, right. So there actually carry flag will not be the same case, right? Okay, so if you actually take the example of -2 and -8 plus of this thing, okay, so can you please help me with the -2's representation? Triple one, 4 ones,
So 4 1 1
1110. Okay, and -8 is, tell me -8, not 8.
So 1 1 1 4
Hmm.
1 then 1 0 0 0.
1000, right? If I hope this is right. One triple zero 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 zero. Then you have two's complement of that 0 1 1 1. Yeah, plus one. Yeah, it should be this. Yeah. Okay. So this is -2 and this is -8. Okay. So in you are actually doing subtraction now. Okay. When you do a subtraction in two's complement, subtraction according to the microprocessor, what it will do? 0 minus 0 is 0. 1 minus 0 is 1. Okay. 1 minus 0 is 1. 1 minus 1 is 0. 0, 0, 0, 0. Okay. So there's no carry out. Okay. In the previous case, what was the case? There was a carry out. Was there a carry out when we did it in a two's complement form? Yes or no? Yes or no?
Sir, isn't there a carry? The
No,
second
there's
step.
no carry. No? That's the point. No? That's the point. No? When microprocessor does it, it doesn't do the two. It doesn't take -8 into two's complement and then add it. It doesn't do that. That's the point. No? There's no in microprocessor will directly do the subtraction. Okay, 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 0 is 1, 1 minus 1 is 0, and so on. You will not get a carry out. Okay, microprocessor will not do a subtraction in the way that it converts into two's complement and then add it. It doesn't do that. Okay, so that is the reason. We have, you can look back at the previous lectures also, in which what we have done is previous lecture in which we have done a subtraction, one subtraction in the hexadecimal. Okay, there you can refer to that. The way we do the subtraction there is what the microprocessor does is directly it will do the hexadecimal subtraction, right? It will not do a, it doesn't convert into two's binary, doesn't put into binary and then take the two's complement and etc like that. It doesn't do that, right? So that is the reason you have a problem, or you will have a difference in terms of the carry flag in the pen and paper method, and or you can say the two's complement method and this particular subtraction. You will have a difference in that, right? So that is the reason why I have brought about this point, is that it's not that always that the carry flag is the XOR of sign flag and overflow flag, right? It's not the case, right? I hope it answers your query, right? Is it?
Are we doing the subtraction here?
Yeah. Whenever we do a whenever it does a comparison, when you say CMP CX comma BX, what it will do internally, it will do CX minus BX. It will not change the contents of CX, neither it will change the contents of BX, but it will actually do a subtraction. CX minus BX it will do internally. Okay.
Yes, sir. Then I think that you written the positive plus sign by mistake, because if we take minus of minus 8 will become plus 8.
That's
Then
what.
in pen paper
Yeah,
method,
it
we
is.
will
It is. Yeah,
again
it
have.
is. Yeah, it is minus subtraction. It does a subtraction. So subtracting -8 from -2. That is what it will do, right? So this is Cx. This is
Okay, sir.
Bx, right? So internally it will subtract it, right? Okay, fine. Let's go further. So write an ALP, small ALP for to find the greatest signed number. Okay, from a set of 10 bytes, and the greatest number must be stored in a location called RES. Okay, so we start with dot model tiny, and in the data we will first declare an array. Okay, the array will be declared in this way, and result is here. Okay, you reserve a byte here. Now, what I will do is I will load the effective address of array into BX, and I will load the count into CL. Okay. So what I will do is I'll first load the first byte into AL. Okay. Decrement CL and increment BX. Basically, the first byte is into AL. Now, what I will do is I will compare AL with the next byte, because now BX is incremented. So I will compare it with the next byte. If AL is jump, if greater than or equal to. So because here I'm using a JGE, I will do a signed comparison. Okay. So if JGE, that means if AL is greater than this or equal to, greater than or equal to this, then this will happen. Okay. So move AL comma BX. Okay, if otherwise, if then it will, if they are greater than or equal to, then what will happen is I don't have to do anything. Basically what I'm saying is, was what AL will have is AL will have the greatest number. Let us say it will start with the assumption that the first byte is the greatest number. So that is what I have put. Okay, now, if at all I find any number which is greater than the what is the content of AL, I will be replacing that with I'll be putting that greater number into AL. Let us say that first comparison I will do this and this. If 91H, if 91H is greater than or equal to 02H, okay, then AL will become 02H. Okay, otherwise the other way around, right? So JGE x1. If at all, if it is greater than or equal to, I don't do anything. I'll just increment bx and then go on further. However, if at all, if it is not greater than or equal to, that means if this particular number is the greater number. Okay, if this particular number is the greater number, then what I will do is I will move that into AL, so that AL will have the greatest number or greater number among them. Right, among them, whatever is a greater number will be moved into AL. So like that, I increment BX, decrement CL, and if until CL is not becoming 0, that means still I have not come to the last byte, I will go back to this particular location, again do a comparison. And in the final point, I will just move AL into RES, the location where I have to store the greatest number. Right? Okay. Right. So that is how I do it. And then dot exit and end. Okay. Dot exit will actually end the DOS mode, and end will end the program. Right. So the next is the program model. This we have already seen it. Yes.
So here, the thing which we have labeled as X1, the two code lines for incrementing BX and decrementing CL. So can't we use the first segment only where we have written decrement CL, increment BX? Does this order of BX and CL matter?
No. Yeah, it does matter. Why? Because see, I'll tell you. See, now I want to actually continue this whole thing. Okay. I want to continue the whole thing until CL doesn't become 0. Okay. If you actually interchange these, what will happen? It will increment BX Now Z flag will refer to or will reflect whatever is the operation you have done in increment Bx. Getting it? So it will refer to whatever happens in increment Bx. Let us say the case is if you actually write decrement Cl and then increment Bx. Okay. So what? Let us say that Cl has become 0 and 0 flag has become 1. Okay. Now what will happen is if I then do it, that is increment Bx, then what will happen is Bx, if Bx will become Bx plus 1, okay, and 0 flag, okay, will refer or will reflect the operation of this one, that is Bx is equal to Bx plus 1. So 0 flag will pertain to this operation and not this operation, and therefore you will get erroneous results, right? So that is why we want it to happen. That we want to, this order is very important, right?
So, sir, in the beginning, before x2 starts, there also
Yeah.
decrement CL and increment BX should be like this only. There
No,
we
no,
can
no.
discuss it, no?
There you can interchange. That's not an issue. There
So
is an issue.
instead of moving to x1 after move AL comma BX, can we directly label that first decrement CL increment BX as x1?
Where? This one?
Yes, sir, here.
No, we can't do that. Why? Because see, what is happening is, I'll tell you something. Now here, the value of ACL is becoming 10 here. 10. Now this became 9. Okay. So you are saying that instead of putting, I remove these two. Okay. Let me erase all these things.
And use those only.
Use those only. It won't be so straightforward, I will say that. Why? Because I'll tell you. I hope others are understanding the question. Her doubt is instead of writing again increment Bx and decrement Cl, I can put this in the right order. That means the program will be move Al comma Bx brackets. Okay. After that, I will say increment Bx decrement Cl. Okay. And then I have this comparison operation. Then I have JGE. And then I have move instruction. And then what I will say is, okay, now I have to go to this particular location. That is, let us say I will put this as x1, right? That is what you want, right? Who was
Yes, sir,
asking
yes,
this
sir.
doubt? Who was asking this doubt?
Sir, Avi.
Avi. Okay. So now instead of this, I put it here. Okay. Now move AL comma BX. Okay. Now, how do I go to jump in this? How will I do this? How will I go from here to here? I should have some condition, no? I should have some condition where I have to go to jump x1, right? So that is not there here. So how
Yes.
will I can do it this way. I can do it this way. If you want, I can do it this way, but I will have to do some this thing like J N or J Z x2 x3, let us say that. Okay. And then what I will do is decrement CL this thing. Then I have a comparison operation CMP AL BX brackets, and then I have JGE X1. If jump if not greater, then go to X1, right? And then otherwise, what it will do is then otherwise it will move AL comma BX. I've moved that, and then I said JMP X1. Okay, and then yeah, and then I have x3 move res comma al. Okay, and then dot exit and end. Okay, so let us explain if, let us see if this also results to, if this is what it will result to, or this will have the same way. Okay. Won't it lead to an infinite loop? Let us look at that soon. Okay. So I have LEABX array and then CL0A. Fine. That is all fine. Then I have move ALBX. That is the first byte is moving into AL. Okay. And then I increment BX. Okay. I increment BX. That means it will actually go to the next pointer. I decrement CL because I have moved already one byte into CL. If CL is now becoming 0 already, then I just go to this particular location, that is here, and then move into RES AL, whatever it is. Okay. If it is not 0, okay, if CL is not 0, then what I will do, I will compare AL with BX. Now, because BX is pointing to the next location, it will compare. If it is greater than or equal to, if AL is greater than or equal to, I will not do anything. I will have to do the next comparison. That is increment BX. So now BX will go to the third byte here. Okay. Decrement CL. Okay. JZ X3. Okay. So now you observe here what is happening is, even before I do a comparison, I am actually checking CL is greater or not. Are you able to see? Let us say that CL value was, let us put the value of CL value as 10 decimal. Okay. Now the first byte has moved into AL, right? First byte has moved into AL, and I have incremented. Let us say that the BX value initially was, let us say, 0. Let us say this is at offset 0000. Okay, for a simple calculation perspective. Okay, 0000H. When I say LEA BX. So I have moved the first byte into AL, and now BX has become 0001, let us say. Okay. Now decrement CL has become 9. Okay. It will check whether CL is 0 or not. Fine. If it is not 0, then it will go to this comparison. That means AL will now be compared to now the 0001. Okay. If it is greater than or equal to, fine. Otherwise, it will move it to the next. Okay. And then you will be going to X1 again. Okay. Now X1, what will happen? BX will now get incremented to 0002 and CL becomes 8. Okay. So this has moved to here. Okay. BX has moved to this and CL has become 8. And then you check whether CL is 0 or not. Okay. Like that, you will be moving it. I'll just change it little bit. Instead of 10, let us just have 3 to actually check it. Okay. So initially it was 3, so that will become 2 when it comes here. Initially it was 3. First byte has moved into AL. I incremented BX, that became 0001. Let me first erase off these things. 0001. First byte has moved already. BX has become 1. CL now has become 2 from 3. If it is not equal, then I will do if it is 0, then it will go to X3. So it will not go to X3. Okay. And then I'll compare compare AL with 0001. Okay. If they are equal, then they will go to, if it is not, if AL is greater than or equal to, it will go to BX. Now X1. Now BX will become 0002. Okay. Now CL will become 1. Okay. Jump is X3. No, it is not 0. Now CL will become, compare AL with BX. Now BX is what? 2. So this will become 2. It will compare with 2. Okay. If jump is equal to or not, fine. If it is, let us say AL always has a greater number. Okay. So it is greater than or equal to. So again, it will go here. This will become 3, 0003. This becomes 0. And then what will happen? If it is 0, then it goes to x3. That means it will exit. How many comparisons you have made? How many comparisons you have made in this?
Only 2.
Only 2 comparisons I have made. Okay, I have taken the first byte and then I have compared with the second byte, then first byte and compared with the third byte. Okay, that is fine. I think this also will be okay. Because CL is 3, the array will have 3 numbers. The array will have 3 numbers, and you have to make 2 comparisons. Okay, the first byte with this, and then another comparison for the third byte. So this also will be fine.
So
Okay.
for a safer side, can we use decrement CL after the CMP command?
You can
Just
try out.
after.
There are different ways. Yeah, you can try out. There are different ways of doing it. You can try it
Okay.
out. Okay. If we discuss the other way, it will, I mean, it will take a lot of time here in the class. So there are different ways of doing it. So I just pursued the one path where, in the sense, one way of doing the alternate. If you want to, don't want to do decrement CL twice, or I mean, different locations. You want to have a single decrement CL instruction. So this will also be right. Okay, so Sumuk, I think now your query is satisfied, right? Right? Okay, fine. Okay, fine. No, then the compare will be the location. Performing subtraction by this way complicates the design. Are there any advantages of using the method in rather than 2's complement? 2's complement will be used for the addition. Okay, for the subtraction, we will represent in 2's complement form, but we will not do 2's complement subtraction as we do in the pen and paper method, Akash. Right? Okay, so let's go further. The program models we have already discussed. Okay, so this is how actually Tiny will look, where all CS, DS, SS, ES all will be pointing to the same 64K location. In a 64K location, you will have first 100 bytes, especially in dot model Tiny. The first 100 bytes, not 100, 0100H. This will have a PSP, which is program segment prefix. So this will basically have the state, basically the status of the program. Okay, what is the current pointer, what is the IP value current, what are the, basically the state of the program will be present here. Okay, in PSP. Okay, different parameters related to the program that will be present in this PSP. In the dot model small, as we have discussed in the last class, you will have 2 segments, one for DS and one for CS. You will have a different segment for CS and DS and CS. Okay, so you will have a, for example, the CS and IP values here, SS DS value will be here. So different data segment here. In this case, both CS, DS, SS, and DS all will be pointing to the same location in dot model small. In Tiny, they will have a different pointer for CS and DS. Okay, and SS also will have a different pointer. Okay, so generally what will happen is the structure of this main is used to actually simplify the simplified segment directives. Okay, so what you will have is dot model small, if at all you have this. Okay, so this statement will be required before you have any others use of any of other simplified directives. Generally these segment directives are used to have a simplified way. Yes, if at all you want to have a separate stack, okay, you can actually have dot stack and declare the values of stack just like you declare the data values, data segment values. Just like you declare the data segment values, you can have declaration in the stack also. Okay, where you can actually define what will be the contents of the stack. Okay, by default you will be using 1 kilobyte stack. Okay, and then you can have dot data where you will declare the data declarations here, dot code and dot startup as we have seen last class, and then you have the program. Then finally you will have dot exit and code, where it will actually exit the whole code. Okay, right. So let us continue with the other aspect, that is we'll be going to the logical and string instructions. Okay, there's not much time. Okay, I'll just start off with this one instruction, that is AND instruction. Okay, or fine. I think we will take it up in the next class only. Right. We will perhaps first finish off the logical instructions and then come back to this, or we will actually go to the jump instructions little more details and then come back to the logical instructions. Any doubts? If you have any, we can discuss. Otherwise, that's it. Okay. So the point was, let me go to that particular slide. Right. So if you actually do, see, overflow will be the same. See, what happened is, like, suppose I'm subtracting minus 8 from minus 2, let us say that, then it will be the following. Okay, triple minus 2 will be represented as 1111 triple 10, and 8 will be represented as 1111 1000. Okay, so when you do a subtraction, when the microprocessor does a subtraction, what it will do is it will do a direct subtraction. 0 from 0, 1 from 0 subtracted from 1, it will be 1. 0 subtracted from 1, it will be 1. 1 subtracted from 1 will be 0, and so on. Okay, it will do a direct subtraction. It will not do the way that we do on in the pen and paper, that is minus 8, it will be converted into its 2's complement and added to minus 2. We don't do that way. Okay, so if you actually take another example, let us say that minus 6 and minus 4, let us say that. Okay, so if you subtract that, 6 will be what? 0 1 1 0. Okay, 0 0 0 0. So the 2's complement of the representation of that will be 1 1 1 1 0, sorry, 1 0 0 1 plus 1. That will become 1 0 1 0. So this will be minus 6. 4 will be how much? How much will be 4? What will be the representation of 4? 4 will be 0 1 0 0. Okay.
6
0.
ones followed by a 00.
6 ones followed by a 00. Right. Is it? 1 second. This is 4. 1 1 1 1. 2 one's complement will be 1 0 1 1 plus 1. Yeah, it will be that way. Okay. So 6 ones followed by is 00. Okay. So when you actually do it, 1 1 1 1. If you add this, okay, so now this is minus 6 and minus 4. If you actually do a subtraction directly without doing any 2's complement of minus 4 and then that, okay, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1. How do I do subtract? 0 minus 1. So what I will do, I will do a borrow. Okay, when I borrow from this place, this will become 1 0. 1 0 minus 1 is 1. 0 minus 1, again borrow. 1 0 minus 1 is 1. Again borrow. 1 0 minus 1 is 1. Again borrow. 1 0 minus 1 will be 1. Again borrow. Okay, so 1 0 like that. Okay, so finally you will actually borrow from here also. So this will be 1. This will be this way. So the answer will be 1111 with a borrow also. Okay, 1111 1110. Okay, so this will be the answer with a borrow also when you do actually the microprocessor way of doing it. Okay, how much will be this be in mine? What is this actually? What is the representation of this? This will be 0000. If you to do that, we'll get a sorry
-2, I think.
minus
Yeah.
two. Yeah, it should be -2. Yeah, it will be -2. If you take the 2's complement of that, that will become this. Okay, so this will be 2 and you have a minus sign, -2. Okay, so this is the microprocessor way of doing where you will actually get a borrow. Okay, if you do a normal pen and paper method, okay, for which I have to take uh, a different slide because this has already become clumsy.
Sir, this does not affect carry flag in any way.
Borrow will actually will mean carry flag will be 1.
Okay.
Right, borrow flag will become carry flag. Borrow flag means carry flag will be 1. Four ones followed by 1010. 4 ones followed by 1010. This is -6. -4 is triple 6 ones followed by 00. 6 ones followed by 00. If you take the 2's complement, if I'm doing a pen and paper method, okay, so minus of minus will be, so for that what I will do, 000000011 and then +1, that will become actually, okay. Now I add this to this, 000, 4 zeros, 10100. Add this to this, 0 1 1 1 1 1 1 1. Okay, so now what is this? This is again the same thing. Okay, the only thing is that I have not got a carry flag again, no carry flag. So here comes the difference. When you do a normal that is pen and pencil method, or this thing pen and paper method, where you actually take the 2's complement of -4 and add it to -6, you will actually here in this case you are not getting a borrow, but if the microprocessor way of doing it, you will get a borrow. That is, a carry flag is 1 in this case. CF is 1. In this case, CF is not 1. Okay, so there comes the difference. Right? Have I answered your query, Ruchir?
So, like in the microprocessor way of
One second. Is it Akash?
uh,
Right. Okay. One second. Her query was with respect to the overflow flag. How is it different with the overflow? There's no overflow. Overflow is the same in both the cases. The overflow flag will reflect the same thing. However, in this case, there is no overflow here because there is no carry in into the MSB. There's no carry out, so both are 0. So there's no overflow flag. Overflow is 0 here. Here also there is no overflow. Subtraction of two negative numbers is leading to a negative number, so not a problem here also. Okay. However, if you, let us say that if you are subtracting this way, that is minus 128, or let us say minus 120 and 119. Let us say that if you are subtracting, that is actually it will become minus 120 minus 119. You will actually get a overflow there. Okay, you can actually refer to that. You will be getting an overflow there, right? Does it answer your query? Yeah, right. Thanks. Yeah, somebody else was asking a question. There's some other question. Right. Okay. If that is all, thanks. Thanks for joining.